Well, yeah, typhoon where? Philippines? Yeah, that would be pretty bad.
Yeah,
This is South Carolina. It's a little different. A little different.
Wait, Dr. West, important announcement. Have to make Piggly Wiggly in Somerville has water.
All right, so for all your hurricane preparation needs, Piggly Wiggly at Somerville has water. I am recording, so everyone in the class will get that announcement. Yeah, so, everyone be safe, but more importantly, pray for the people in, Haiti who don't really have homes that, can survive a hurricane.
And they're getting hit by the class 5.
Class 5.
We're down to class 3 already, so.
Yeah, or even lower. But
We're running systems.
well, we have no idea, right? We don't know yet.
I mean, we get a library.
We believe things
If
are
we
coming.
get hit.
If we
3 or
get-
less.
This is the last chapter before our midterm, right? Chapter 6.
Wait, what?
Or the last chapter of section 1.
Yes.
A little bit.
Yeah, well, I put in sections 1, 2, and 3 because I'm importing this course from Gary. He did 3 exams, and I do 2 because 3 is just way too much work.
Yeah, it is.
It really is, isn't it? Thank you, Matt. Got my back.
Yeah. And it's odd.
And it is very odd. Terribly odd. Whew, that was a bad pun. So we're going to go in today and talk about, now that everyone got the hurricane business out.
Do you hear there's another one right behind it?
Yeah, is it coming right for us?
Yeah.
It's coming right for us?
It's going to hit this hemisphere.
All right. So today we're going to talk about process synchronization. This is very important, although I don't know how hard this will be to understand. Really, you just need to make sure all your processes or your threads can somehow synchronize with one another to not, mess up each other's work. We'll talk about more of that, namely not have a race condition, and there's different ways to fix it. All right. The classic way to talk about this is the dining philosopher's problem. Have any of y'all seen this one before? No one?
Yeah.
No?
Yeah.
Yeah? So what's going on?
They all have the forks, but if they all reach.
Well, in this
the
version, they got
forks-
chopsticks. Oh.
Wait, so is it like one chopstick each? Because that changes things a lot. Oh, yeah, that does change things.
Well, it's also one fork on each
Well,
side.
they also need.
Right. So the
Some
idea
chopsticks.
is each philosopher needs to eat and think. Now, I've learned that this is a severe weakness of philosophers. They have to think in order to survive. Other people don't have this issue in life. But so they need to both eat and think, which is a terrible way to exist, but that's okay. But each philosopher must use 2 chopsticks to eat. All right, wow, these people, well, they're philosophers, right? They can't do it with one. They need both from each side. They probably use both hands as well, or something crazy like that. There is 1 chopstick between each philosopher. So, given, we'll say, more than 1 philosopher, how can we come up with a scheme in order to ensure that each philosopher does not starve to death and also does not die from not thinking? There we go.
Ask the waiter for more chopsticks.
Okay, so you would add a waiter for more chopsticks. That really is a great solution. But the other part of this problem is let's pretend that there are only that many chopsticks in the entire universe.
Ooh.
And for some reason, this bowl of rice has like a little something above it that constantly keeps putting food in it for them, so it keeps the bowl full. I know. And these are philosophers, so there's no way they're going to be able to actually create something like a chopstick. That is beyond their capabilities. And there's no, well, we could have a waiter, but let's just say he's not an inventor. How about that?
Give one of the philosophers a gun.
Again, they don't know how to use it. They're a philosopher. Come on, have you ever met a philosopher?
Aren't you one?
I guess in a way.
You don't use chopsticks?
I do use chopsticks.
So let me get this straight. One of the most complicated eating utensils in the world they can use, but they can't pull the trigger of a firearm.
It's a stick.
I never said they couldn't pull the trigger on a firearm. You're implying that they can pull the trigger and aim it in the correct direction while still having a bullet in the chamber at the time that they pull it. Though that's a lot of ifs for these philosophers, okay, man?
And find the safe.
And then they gotta find the safety.
Obviously, these chopsticks don't have the cheater things on them because they're already separated.
Right. Well, someone had to do that for them, right?
Well, that's what I'm saying. They're not using cheater chopsticks. So
Correct. The regular ones. All right. So how do we solve this problem?
All right, going back to last semester's answer, prioritization.
Prioritization. Okay. How would you prioritize? What do you mean by prioritize?
Well, if I'm one of the philosophers, I'm first. If I get to set the priorities. Well, let's see. You have 5 chopsticks, and you've got how many philosophers? 5 philosophers, but you need 2 chopsticks to eat. So only two processes or 2 philosophers are eaten at any one time. So
Hopefully.
What's that?
Hopefully. Could there be a situation where none of them eat and they all die?
Yes.
Yes.
Yeah. So if everyone picked up their chopstick on their left, then no one could be able to pick up a chopstick on their right, and then they would die of starvation. Wondering what just happened.
So you need to start by randomly choosing who gets to eat first then,
So we're going to choose who gets to eat first.
as like the first step.
All right. So the issue with this is you're assuming there's a waiter that can tell these philosophers what to do. Now, I'm going to go ahead and take this to the next level. Even if there was a waiter, philosophers are not going to listen to them. They're philosophers. They're going to do what they want to do.
Okay. The first 2 that get 2 chopsticks, let them go for chopsticks. The
Well, but
first
that's
2
the
that get
problem.
2
What if all
chopsticks-
5 of them pick up a chopstick at once on their left, and now there's no more chopsticks on the right to eat?
Then system interrupt.
System.
Because the
Philosopher
processors
0 pick up both chopsticks.
Okay. So each one of them are going to number themselves. All right, that's fine. Each of them can be assigned a number.
Philosopher 0 pick up both chopsticks.
What will the other philosophers do?
Wait.
Think. Oh, okay. So, all right. So he picks up both. Then what does he do?
He eats for a specified amount of time.
Okay.
Then he has to put chopsticks down.
Oh, he has to put them down. Okay. Then what does he do?
Philosopher 1 picks up both chopsticks.
Okay.
He eats.
Oh, so
Everybody
you're
else-
like a token ring where whoever
Yeah.
has the token can have access to it. Okay.
And
Other
you
than
couldn't
this-
do 2 of those at once.
I was going to ask, is that the most efficient algorithm?
No.
No, because up here, like Matt said, there's 2 of these that you can do at once. So we're going to try and figure out if we can come up with a way to solve this problem and help some philosophers out from not starving to death. Okay, so objectives, critical section problem. It is important when you're doing multi-threaded programming or multi-programming that you think about the critical section of your code, which is really just the part that can actually intrude or have race conditions with other processes. Yes, John?
Okay, well, I was just saying, in the solution to have 2 at once is to have 0 and 4.
Right, so 0 and 4.
0 and 4 eat, then put their things down, increment, then now it's 1 and 5.
Or you mean 0 and 3 and then 1 and 4?
0 and 3, yeah, because we go 0 and 3, then 1 and 4.
Yeah, you can do it that way
and then
too.
just keep rounding.
Does that, let's see, does that equally load balance it? I think
Wait, no load balancing was thrown in there. Is the table going to fall? over?
well, I'm
I'm
asking, is it isn't an optimal solution?
No.
It might be for 2, but it won't be for, it might be for 5, but when you go to 6, you could have 3 people doing it. So you gotta keep figuring out how to
okay.
rotate it and whatnot. All right, so we're gonna present both software and hardware solutions. Most of the time what you need to understand is that the hardware has to have some built-in support in order to actually give you a good solution. What you learned in architecture is, in general, not going to suffice in order to solve these problems. We do need to add an extra piece of hardware. We'll talk about that. And really what it comes down to is the idea of an atomic transaction, which just means that this whole transaction, you guarantee that all of it occurs essentially simultaneously. All right, concurrency, access to shared data may result in data inconsistency. Why is that?
One uses it, the other doesn't know.
Right, so race conditions, essentially. So we need to maintain consistency somehow. So here's an example. We want to provide a solution to customer-producer problem that fills all the buffers. We can do so by having an integer count that keeps track of the number of full buffers. Initially count 0, so it's incremented by producer after it produces. All right, sure. Okay, that's a weird example.
We just kept the rice bowl full.
We just kept it random. All right, so here we go. Producer. Produce an item and put it in the next produced. I don't recall. Remember, producer, consumer. The producer's giving something out to the consumers for them to do something with. So in here, the producer's the rice bowl. Right. So while count is equal to the buffer size, do nothing, aka the buffer's full. Then if it's not full anymore, put something in it, increment in, and then increment the count, and then you basically go back and try and fill it back up. So this is while true. Everyone see what's going on there? Consumer, aka keep spinning. If the count is 0, aka the buffer is empty, do nothing. Otherwise, go grab something, count minus minus, and consume the next item. All right, so what's the problem here if you have one producer and we'll say 10 consumers?
You could all grab the
Not
same
enough
thing at the same time.
chopsticks.
Yeah, well, this doesn't actually go correctly to the because the consumer, they could all instantly say, oh, counts 1, all right, let me go grab it, and then increment out, decrement count, and they'd all be working on the same piece of data, which is not good.
Well, wouldn't you put in there, you have to make sure they get something. What happens if everybody goes there to grab,
Mhm.
right? Are we assuming they're copying what's in there? Everybody's using it, the thing stays in there and everybody grabs the same thing? Or are we assuming the first consumer, as soon as they get something out of there, there's nothing there for anybody else to grab?
This code is wrong.
Ooh.
Okay.
That was the point I'm trying to say. This code is wrong. For more, when you have more than one consumer, this is incorrect code, which is the whole point of this whole thing anyways.
Okay.
So,
It's like it didn't make sense.
yeah, because if you have 2 consumers, count as 1, they could both jump out of this while loop at the same time, grab the same piece of information, increment out both of them by, well, 1 or 2, or maybe, who knows, decrement count, maybe they both by 1, or maybe it does net 2 or something, and then go on. So you're actually doing double work. So this is not correct. All right, these slides like to go through a long explanation of what a register is.
Never heard of one.
Never heard of one during computer architecture, did you? Not a clue. Okay. Since you all know what a register is, I could skip this. Just realize that that is the basically the fastest memory, so to speak, in a CPU. So the race condition that they're going to go through and try and explain the best is usually count plus plus, register 1's the count, increment it, and then put the count back out, minus minus, again, grab count, decrement it, put it out. So the problem they're saying is consider interleaving it with count equals 5. We'll say count is 5, register 1 equals count, register 1 equals register 1 plus 1, so that's 6. But then afterwards, S2 executes register equal count, so now it's 5. And what we got is 4, and then now we have count equals register 1, which count is 6, count equals register 2, which is 4. Okay. What was the issue with this? Oh, the issue here is that they both went to decrement count. Or wait, one went to increment count, the other went to decrement, but only the decrement actually happened in the end. That's what's happening here. So this is a race condition because one's trying to increment it, the other's trying to decrement. The final count should have been 5 because one incremented the other decrement. But instead, there's since namely S4 occurred after line 2, then that means S5 ended up being 4 instead of 5, which it should have been. Do y'all see that?
And that's the order in which it went. 1, 2, 3, 4, 5. Is that the order in which it went?
Yeah, we're saying that in this example, this is the what would happen. Let's say this was the order when 2 processes were executing, because it can happen either way. I mean, it can happen in any order, really. Okay. So the race condition is, since you allow both threads to manipulate the count variable, you have several accesses. All right, the outcome does not depend on order of execution, then no race condition exists. This occurs all the time in OSs, namely these race conditions back here, where we're trying to, the idea is who's racing to actually get the value put out first. In this situation, it looks like the yellow did it. Yellow did it. I grabbed the data last, but overwrote it last, which is why his value is what resides. The problem is, essentially, these 3 blue should have all occurred before yellow did anything. But since they didn't, it's kind of a race of who can get to it first.
That was all in one processor?
This is on 2 separate processes.
Separate processors. So
Well,
one-
technically, we're going to say 2 separate processes, because this could be a single processor where they just did a context switch here to here and started executing another process. The same problem would occur, but it could also be 2 separate processors.
So the blue is one process and the yellow is another process.
You got it. So this can cause a lot of unexpected behavior, which is bad. Here's the part of the process that accesses the shared variable is called the critical section or sections. So that's what's important. But basically, the part that can cause race conditions or issues is called the critical section. All right, so the solution to a critical section problem, what's the problem? We want to make sure that when someone enters the critical section, no one else enters it as well.
So you have to identify them to begin with.
Yeah, you got to identify them to begin with. And that's first off, we want to solve basically mutual exclusion. If one process is in it, no other processes are. 2, we want to make sure there's progress, because the simple solution of this is, okay, no one ever enters the critical section. We still want work to get done, so we still want to have some type of progress in it. So we got to at least be able to jump into it. And let's see, bounded waiting. A bound must exist on the number of times the process are allowed to enter after a process. Okay, so this is just a way to do load balancing, essentially. So first off, we have Peterson's solution, which is a very simple solution for 2 processes. Assume load and store instructions are atomic. All right, here's the first time we have this word atomic. That means once you hit a load, the load of something, any amount, you cannot be interrupted, and no one else can try and load or store from that memory location while your load is executing. That's what it means. So the load and the store are the critical sections, and we're assuming that only one process can get to that piece of memory at a time. So they share 2 variables, int, whose turn it is, and boolean flag, which is basically to say, well, there you go, turn indicates whose turn it is, and flag indicates if the process is ready to execute. So flag sub I true implies p sub I is ready to go. All right, so for process, if your flag I equals true, why? Because I'm ready to execute. And turn will equal k. Where did k come from? Oh, awesome. Great. Okay. K. So you're signaling, hopefully what you're signaling is it's the other person's turn to actually execute. So while the other guy is ready and the turn is K, the turn should be me. In the critical section, afterwards we're no longer ready, and you keep going. Wow, that is confusing.
Where did you get K?
Yeah, it doesn't tell you where K came from. Huh. Okay. Key thing to get, K must be referencing the other process here. So it's saying while the other process is ready and it's its turn, do nothing. So remember there's a semicolon right there. So it's spinning, doing nothing as long as it's the other person's turn and he's ready to execute. Once he's done, now I can do my critical section, because supposedly he has set the turn, basically given him the token back, and then, or set himself to false. The other process. You do your critical section. When you're done, you say, I'm no longer in my critical section. I can do whatever I want, and then continue on. So it's kind of flipping back and forth. The trick to this is implying that basically the load, the turn is atomic, as well as the storing a flag. All right. While technically this works, what are some issues with it?
There's only looking at one other process right now.
Right, so works for only 2 processes. That's one problem.
It's his turn, but he's not ready.
If it's his turn, but he's not ready. His turn, but he is not ready. Oh, so he has to finish doing his remainder section and then give the turn back. Yeah, so he may have do a lot of extra work before giving up the critical section, is what you're saying? Don't know?
It's a bit weird that you say that it's the other guy's turn at the start of your process. So what's the other process look like?
It's the same thing.
Okay, so then
So
you're
it's
just
just-
telling each other that it's their turn.
Yeah, so
Yes,
I may be
it's
0,
fine.
K is 1 for one of them, and the other one I is 1, and K is 0. Or did I say it backwards?
Wait,
Okay, so K isn't always.
well, that implies, when I look at that, it seems to me that you got flag K and turn equals K. Now you're in the critical section, so your process is in there.
No. While the other process is ready and it's the other process's turn, do nothing. That's that semicolon right there. It's going through that while loop, constantly checking, is he in the critical section? Is he in the critical section? If he's in the critical section, I'm just going through this while loop.
Then why do you have, okay, then the next, now in the critical section.
This is semicolon means do nothing during this while loop.
Okay.
And then you go into the critical section once it's your turn, and then you signal that I'm no longer in my critical section. Basically, what you do is, before you go into your critical section, you give the other process all the credentials to go into theirs, and then you start checking to see when the other process gives it up.
Okay, you just said flag I equals the truth.
That's me.
That's the process we're in,
Piece of I.
piece of I.
Yeah.
And piece of K is the other one.
Okay.
It's a very courteous program.
It is.
I'm ready, but you go ahead.
You're right.
You're telling each
Yes.
other-
All right, now that you're done, I'll go.
Right.
Okay.
And then he gets done with his. Well, I'm ready again, but you go ahead and go.
Well, it does make sure that each process is ready to go into the critical section.
Right.
Won't be wasting time.
Yeah, the point is you ensure that the other person's not going to the critical section by letting them go first.
But so, okay, so when they get out of theirs, though,
Mm-hmm. Maybe we should write some numbers.
because their flag is ready. Yeah, no. So I've just set turn equal to K to them, right?
Wow, we need to fix this board. It's kind of bumpy.
Yeah.
So I, and then K, just so this is clear. I for this guy, of course, is 0, and for this guy is 1, and then K we're going to say is 1, and this guy's 0. All right?
All right, so I go in, I set my flag true, saying that I'm ready, and I say it's your turn.
All right, hold on. So we're going to have flag equal to, and we're going to start with 2 falses. All right, and then turn, we don't know whose turn it is yet. All right, so who's doing what first?
Both processes at the same time?
Both processes at the same time. So
Isn't
both,
that the idea?
yes, but in technicality, they can't be done simultaneously.
Okay.
One has to go first before the other. That's just an offset of how computers
Okay,
work.
worst case scenario. Flag I equals, flag of 0 equals true.
All right. So that means that P of 0 is up here.
Sure.
All right. Then he's going to
Interrupt.
Okay, interrupted.
Flag of 1 equals true.
P0 is right here. All right, flag. Okay. It's true. So
Interrupt.
now, so now we're going to interrupt. Okay.
That's what I said, worst case scenario.
So we're going to do P sub 0 and P sub 1. So he's currently here, and P sub 1 is currently here. Okay. Now.
Worst case scenario.
So you're
Now,
so now he gets.
P0 turn equals 1.
Okay. All right. So. Okay.
Interrupt.
It.
Worst case scenario.
All right. So now he's going to go over here, and turn is equal to
0.
0. All right. Interrupt.
I don't know. I'm trying to figure out what the worst case scenario is going from here.
Well, now they're both here. Only one person is going to get a turn, right?
Yeah.
Who's getting the turn?
Whatever the last flag was set at.
0 and, 0.
P0.
Zero's gonna get the
Yeah,
turn no
because
matter what.
no matter if P1 can go here and keep executing, at some point he has got to give up and allow P0 to actually execute the critical section.
And
So-
he's gonna get in there and flag is true, but turn is not the other guys.
Right, it's not the other guys. So because of that, P0 will be in his critical section.
Okay.
All right, now when he's
He goes
done,
down.
now he's going to go down to here, at least to here, and then we'll say he got interrupted, right? Right after the flag. So then flag sub I, which is his, would go to false. And now we could go either let P0 continue or tell P1 that now he can enter the critical section. He can update the flag.
Because flag of the other guy is false.
Right.
Wouldn't P1 have gone first? Because you gave K 0 to P1.
Okay, hold on.
So the turn is set to 0 at that time.
It's
First
still
time.
set to 0, but notice it has to be, both of these have to be true for it to do nothing.
The flag should be true for both, right? At the
Well,
start.
flag of K is true, or is, I'm sorry, remember on P1, K is 0. So flag of K
Exactly.
is false, so it would gone out of his while loop and now he would be in the critical section.
I mean, in the very first time when they both first hit the while loop,
Mm-hmm.
K 0 is P1. Let's see, so turn.
Say it like K, P1's K or P0's K. Say it like that so I understand what you're saying.
P1's K
P1's
is
K.
0 in this case. You flip them,
Right.
so
P1's K
wouldn't
is 0.
P1 start?
So but if P0 was up here, this flag is still true.
Mhm. I mean, like roll it all the way back to before either of them enter a while loop at all, and then.
Oh, which arrow? Like right here?
Yeah, they're
Okay.
both there.
All right, hang on. They're both there. Hold on. That and that's the state.
Yeah.
That should be the state. Okay.
So turn 0, wouldn't it be P1's turn at this time?
No, because,
Oh, you're right. I said this backwards.
Okay,
Yeah,
I just
you're
wanted
right.
to make sure. I
You're
wasn't
right because
confused.
because K turn equals 0. You're correct.
Yeah.
So
Just
P-
because you flipped them, it's fine.
I flipped them. It's still going to do essentially the same thing.
I want to make sure I wasn't missing something.
Yeah, no, and then P sub I here would be false. Right, and so P sub 1 can continue on. Thank you. I said it backwards. I need my camera.
And
I found it. I found it eventually. My 1-year-old hid it. It was all tangled up.
No. Flag of 0 was true. And turn was 0. So P1
So that's
waits.
the other person's turn.
Yeah, so P1 waits.
No.
Oh, no, K. Right. Because we keep doing this. All right. Fine. Let's think about this.
Yeah, explain it to me if it's not.
we would write this code
Okay, so
differently.
remember which one you're at. If you're on P0, flag of 1,
Both flags are going to be
yeah,
true.
both are true. So that's fine. So we're looking at turn.
Turn of
If you're at
K.
P of 0, turn is 1. That is not true, so he will not wait.
Yeah, so P0 is not going to wait. But P1, on the other hand, K is 0, so he would be
Oh,
going.
it's inverse. Yeah. Okay. I
Whatever.
see.
I could put not equals over here and then do the same thing.
Yeah.
All right. And then once you're down here, P of 0.
Got it.
Okay. Any other
Getting the
cases
same
here we want to look at? No? You
If-
sure?
So now P0 completes.
You want
Goes
P0
back
to
to
go all
this-
the way back up?
Yeah, P0 goes back through.
Goes all the way through, comes back up. His flag will be back to true. And then before he can go to this while statement, he has to change the turn.
Okay.
So then the turn becomes 1. And therefore process 1 is now allowed to go.
Except if he gets interrupted right before turn.
Right. Well, if he gets interrupted right here,
The state has not changed.
we're still here. He can't go into the critical section yet. He's still spinning, and then back
The other guy will change turn,
Eventually
and
has
then
to
we'll go
take-
back to-
yeah.
Okay.
because there's always
Okay.
progress going by the operating system.
No, that makes sense.
So it'll always flip back and forth between who's in the critical section too.
Right.
Yeah.
Okay. So first problem. This only works for 2 processes. That is a pretty big issue. What's the other actually really bad thing about this?
what happens, oh well, never mind.
The
It's
two
supposed to
process
be
thing
ready.
is actually the biggest issue, but there's another one that's actually pretty bad. What happens during the while loop? When P1 is in the while loop,
It's waiting.
it's, well, how is it waiting?
It's just spinning.
It's spinning, so is it doing any useful work?
No.
No.
You should put a sleep 0.
Yeah, you should, well, yeah, you should sleep it or yield it or something. So that's another problem with this solution, is that it's in a spin lock, is what it's called.
But
where it's
if
just
you,
spinning.
but if you did that, see, like you said, it's only for, it's a offshoot effect, it's two processes. Because if you put it to sleep, then, hey, process number 3 gonna pop in.
Which is
Yeah,
fine.
and then you'd be
Well, if
fine.
it's one processor, then you're just telling, okay, let this other guy keep going. Hurry up and let him
Yeah.
finish, you know? But that's not what's going on here. All right. Anything else before I erase this board?
So adding more processes though, all you would have to do is just add more flags.
And then you have
And
to
then
check
you change turn
all
not equal to K.
you have to change all the flags.
Or turn not equal to,
Well, no, you'd have to check
To
the
I.
turns as well, but you'd have to somehow check them all simultaneously.
but you just change turn to not equal to I.
All right. So let's go and figure out why bad things happen when you add a third process. Hey, you did it, not me. Sorry, people at home. And here's K. What is this K?
I have a question. Will they be able to see your drawing on the board, or it's not lit up?
Oh, they're not saying this on the video.
Oh, they're not seeing any of it.
Oh, no.
Oh, sorry.
Yeah, like I said, I need to get my video camera. All right, so we got I. K. What are you gonna have K be? Ooh.
So while not flag I
Well, we got,
or turn not I.
so you probably want to have K. So
Don't even need a K.
don't even need a K.
While not flag I or turn not I. So in other words, when you're not ready,
Oh, I see. So you're gonna change
Or-
this algorithm so that it says
yeah, when
this
you're not
instead.
ready or it's not your turn, wait.
Like that.
Yeah.
Okay. All right. Let's see what happens. Oh, this is gonna be great.
There's going to be 2 at once trying to get in there.
No.
Yep.
Yeah,
It can only
because
be
you said
one. It
not
can
I.
only be one person's turn.
No. No. All right, let's do the.
Okay, can only be one.
Whoa, 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 whoa.
See, because what will happen is, let's say 2 processes have gone through. The 2 processes will have the same.
All right, so then we got true for all these.
Yeah.
And what do you want turn to be? It can be any 0 through.
That's the problem.
We'll have
I haven't
turn.
figured
We'll
that
just
part.
have turn equal to 2. All right, turn not equal to 2. Which processes can jump in?
Only 2.
1 and 0. Turn does not.
0 and 1 have to wait because it's not their turn. Turn is not equal to themselves.
Turn and turn does not equal.
Not and, or.
Oh, now you're gonna change this to an or.
Oh, that's what it said, or.
Okay. That changes things. All right. So now I gotta do a different. So
And it
while
was flag I, not flag I.
it's flag.
Not flag I.
Oh my goodness.
I said all this.
Okay.
Okay. Not flag I or.
Is this
turn not
confusing
I.
enough yet? This is,
So if you're not ready, wait. Or if it's not your turn, wait.
okay. All right. So let's continue on. So if you're not ready, well, everyone has to be ready. Or it's not your turn, keep going on forever. So right now it's P2's turn. Okay.
Wait, but as you just said, you started off, everybody is ready. So while not ready. Is that where we went?
Yeah, while not
ready.
Okay.
Which honestly is probably superfluous, but
All right. Let's do this then. What's right here? turn is, what's K? You said it was I? Okay. So when we're here, we have false, false, true. I'm ready to go. Because it's, and turn is, turn is not I. Okay, so I'm not ready to go yet, correct?
Right.
Okay. Let's do P1.
Except I didn't say turn equals on. I hadn't figured that part out yet.
Yeah, because right now
Can't be
you're.
I would say I plus
K. You got rid of K.
I would say I plus 1 because we want to keep the courteousness going. You can never say that it's your own turn.
Okay.
I
plus
plus
you
1,
probably
and
want
I
mod-
is greater than the number of processes.
Mod big P.
Yeah.
Okay. Okay.
This is, I'm gonna have to write this out now.
All right.
It's not gonna be on a 10.
Yeah, I think.
I think I know what the exam
I think
question.
We'll need the same thing after flag I, though. We're gonna have to change the turn.
All right. Can you see you're chasing your tail here? Because we're constantly finding issues with different ones.
Just saying it was doable.
It's not. You might be able to find something, but I highly doubt it. All right. Because I come up with a situation. Looks like right here. He's going to be here. It's not his turn,
So he waits.
so he waits. And then we're going to have. What are we going to have? We'll have P1 go to here, changing this to true, and this turn to 2. So now he
enters.
can go in. All right, and we'll say he's interrupted right here just for the fun of it. No, we'll just say he's in the critical section for now.
Yeah. Same.
And then 0 goes in, sets
He
his
changes the turn.
true, and then changes the turn to 1.
Yep.
And now P of 1 can also go to the critical section. There.
Second
And
one.
P2 never
That
left the
means-
critical section.
Yeah, we're saying P2 never left the critical section.
Bad things happen.
All right, we can keep going through this. We play this game a lot. Basically,
Or
This-
you take the turn equal.
All right.
Move it only to the end. You can only change turns when
all right, we're gonna
somebody's
stop
done.
now.
That fixes it.
I may fix this situation, but I bet I can find another one.
Let's just get
The
through
door is over
it.
there. All right.
How many kids you said you had?
How many what?
How many kids you have?
3.
Their ages?
Really, it's only the 6-year-old girl that is the problem.
You're recording, by the way.
That's fine.
She's having babies.
No, they're all great kids. Anyways. And yeah, the more serious problem is it only works for 2 processes. The book says it, therefore it must be true. Right?
No, we've already proved
I mean,
it.
that's right. I've already disproved that. Huh. I guess I can't use that anymore. Oh well. So there's definitely far better solutions than Peterson's problems. All right, so we need to come up with some type of synchronization hardware to help us out. Many processors provide hardware support for critical sections. Yep. You could use interrupts in unit processors, but doing interrupts and trying to bounce back and forth in a multiprocessor is pretty time consuming. So what we have is some atomic hardware called it's an atomic memory operation, aka cannot be interrupted. So
Basically, once it's in the critical section, that's it. Nobody-
Yeah.
nobody can touch it.
right, but the critical section is one instruction, so that whole instruction is going to execute completely before you can context switch, essentially, is what it's saying. So the hardware says, even if the kernel tells me to context switch, if I'm still executing this instruction, I'm going to wait for it to complete before I allow the kernel to come in. That's basically all it's saying.
The operating system does that?
No, the hardware does that. The hardware, basically, what it does is once I execute an atomic instruction, I disable all interrupts, all traps, until this instruction completes. So the idea, hey, look, it's locks. Acquire the lock, critical section, release the lock. Everyone good? It's like a key, lock. Okay, good. So, definition of test and set. All right, keep in mind that this whole section is atomic, meaning once it starts executing, it's not finished until the function returns.
What tells us that?
What do you mean what tells you? I'm just telling you that this, what the slides are doing is showing you the code, the C code of what test and set does, and I'm telling you there's an instruction that does this specifically atomically. All right? So test and set. All right, so what do we got? We create a temporary Boolean that contains the value in the target. We set what's at the target to true, and then we return our current Boolean. All right, kind of a little weird.
We're setting the target to true.
Setting the target to true, and then returning the previous value.
When we set the target to true, we're actually setting the value.
No, RV is a temporary value on the stack of this function. So it's a temporary value of the current value in target. Then we set the value at target to true, and then we return what was up here, aka target, before we set it to true.
Okay.
That's not right.
So test and set, because it's like you're testing what its current value is and setting it at the same time.
So what would the use case of this be?
That is a great question. I'm glad you asked that question. All right, so how do we do that using a lock? While test and set of some lock, do nothing until it comes back true, aka you can test and set it, your critical section, then release the lock.
When would test
No, no,
and
no.
set fail?
Well, when it's false, you would do the critical section.
When it's false, right, when it's false. Oh, thank you. So, your question is, when would it be false, or when? So if
When would
the
it not? When
if
it
the old
returns
value is false and I
okay.
changed it to true, then it would keep going. But if it was still true the whole time, it would just keep. Let me say it again. If the old value is false, it set it to true, and then exit the while loop. But if it was
Return
true
false.
Return false points.
Yeah,
Once.
return false.
and then because it would test and set. So in other words, only one process can go from false to true, is the point here. And then later on, of course, that process can at any time release the lock just by setting the lock back to false. And then some other process, who knows, of the pool can finally grab the lock.
But what happens if it gets interrupted right after the while statement?
What do you mean? Right in here?
So it was told, well, no, okay, I guess it would still be true for everything.
Yeah, it's still, everyone else would still be spinning until
Go
it
back
finally
into
released the
test
lock.
and set.
Yeah, remember, this is atomic, so all this happens without, you can't be
Okay.
interrupted in here. This
Okay.
cannot be interrupted.
Okay.
It's atomic, you cannot be interrupted anywhere in here.
How do we
And-
know that?
Because the hardware specifically makes it atomic. Like I said, the hardware says, this is
We
one,
don't
this,
have to do anything code-wise.
no. Well, code-wise, the compiler generates the atomic instruction, and then the hardware says, I'm disabling all interrupts and everything while this is executing.
Do we specify if it's atomic in code somehow, or does
By
the compiler figure it out?
choosing the set instruction that we already know is atomic on there.
And it's going to standard we're going to eventually go to pthread and utexes, and that's a library, a standard API that the compiler takes and then generates, depending on the hardware, if it's test and set, maybe a test and set instruction on the back end. So it's a standard API way of doing things.
Okay.
But the compiler is going to generate the appropriate atomic instruction in your code. Great question. Anything else? All right. So what is the significant advantage of this over Peterson's solution?
It can work for any number of processes.
All right, so any number of processes, any number of processes. Yep.
But if your atomic code is too long, it will make it seem like your computer's only running one process.
Sure. But that's a separate issue on the programmer, right? All right, so test and set. Another one is swap. again, this is atomic, so you cannot be interrupted while executing this, is the idea. So yeah, this literally, whatever the two booleans are pointing to, grab the old one of A, overwrite A, and then B is the new one. Put in there. Cannot be interrupted. All right, how we do here? So while key is true, swap it. All right, so your key is true. You're trying to swap it with the lock. Right, so you're constantly trying to swap it with the lock. Namely, you're trying to grab, some process is trying to grab someone else's false and put it into their key. Right, so then that key would be false and it can go into the critical section. Think of it, you got 10 processes. All the locks are, well, there's one lock. There's one lock, but they all have their own key, right, to try and get into it. Someone, when they call swap, that means one person atomically is going to be able to swap his true with the lock's false, and then he's going to be able to jump out of the while loop and continue until he releases the lock, and then another process can do the swap and continue on. Kind of doing the same thing. Okay, wow, bounded waiting with mutual exclusion and test and set. I didn't see this one. I'm waiting is true, my key is true. While I'm waiting and add the key, test and set the lock, aka you're trying to grab the lock because you're waiting in your key. So you're trying to wait for someone to give you the lock down here. So after you grab the lock, you're no longer waiting. Okay, that's fine. Critical section. Then what are we doing here? Next current plus 1, while next is not equal to current, and waiting to next plus 1% in. Okay.
What does this add to the test and set? Which is supposedly bounded waiting.
Bounded waiting.
I don't think it
There
changes.
can only be so many processes waiting.
Right.
It changes test and set. It's just implementing it.
It's just using test and set.
Oh, okay.
Is this? I cannot see the code from there. Let me look at my screen. Current plus 1% in. Well, next is not current and not waiting. Next equals, all right, so we're just looping through all the next. Is this trying to, okay, so we have a current variable, and that's who I am. Next does not equal current and not waiting. Okay, so the trick here is if next is current, I'm false. Otherwise, waiting next is false. So, so the point here is that someone else cannot be waiting. Huh. All right, well, I have failed you all.
No promotion.
No promotion for me. Semaphore, great, good. We can finally get to semaphores. So what are the problems so far is that we've been going, all of them have been going into a spin lock. Namely, once it's not allowed to enter the critical section, it just keeps executing over and over again. So that's kind of a performance hit. We can call thread.sleep and put it back on schedule. That's a very common way to do it. And that's what really is going on, but we're going to use something called a semaphore to make it more theoretically official. So semaphore S, it just holds an integer value. There's two operations. You can wait or signal. We used to call it P and V. We're going to keep calling it P and V? No, we're not. Okay. Can only access via two indivisible atomic operations, namely wait and signal. Wait and signal. So you're waiting on S. Think of it as requesting S. So while it's less than 0, no op, and then you can try and if you something? Okay, you need to tell us how this works first. Signal S, tell you that you're releasing it by incrementing.
So we're decrementing.
Yeah. Please tell me you do the whole implementation. Oh, thank you. Wow. Why is it all those slides just to get to the implementation? So wait. It decrements its value, and if it's less than 0, add this process to the list and then block. Mainly, aka go back on your queue. When you want to signal, you're incrementing it, and then if, what we got here, less than 0, remove P from the list and then wake up P. What this is doing, you can think of it as extending test and set, such that when you find out down, well, when you try and grab the lock, but you don't have permissions yet, you go into a list where you specifically wait. This is a little better than going into the wait queue, because this is a specific queue the operating system knows about, or the user, whoever's doing the thread scheduling, saying that these guys are all waiting on a critical section to finish, so they're never going back and context switching. Later on, when you finally release it, you say, okay, if my value is high enough, then I can go ahead and wake it up. That's what's going on here.
Wait, so if your value is less than or equal to, then you can take a wake it up.
Yes, because you've your semaphore's integer has gone up high enough. Now that we have,
Oh, okay, so we were decrementing it, but now we've increased it. We're increasing
Correct.
the value. Okay, got it.
yeah, because if you, the idea is it would start at 0, and so, or it actually would start at 1.
You decremented there. It was less than 0, added to the list. And then we want to implement it.
And then you block. Otherwise, if you're good to go, you're just going to keep continuing. So, semaphore. All right, counting semaphore, not used too much, but integer value can range over an unrestricted domain. This is if, I guess, you want to have 2 processes in the critical section. It doesn't really make too much sense right now. So usually it's some type of binary where you only range from 0 to 1. It can be simpler with the Boolean value. Well, actually, the counting one is when you have multiple processes, is what I should be saying. You can implement counting. All right. The idea is you wait on the semaphore. We're going to call it mutex here. Do your critical section signal. Lock, unlock, same thing. All right. Must guarantee. Could have busy waiting, but we don't want to anymore. So that's why we have our 2 additional operations. Block puts it on an appropriate waiting queue, and then wake up to remove it. Any other questions?
So we had counting. What was the other type of what was the other type of semaphore?
Boolean, 0 and 1.
Okay. And did you say, you first said that counting was not used that much, but you meant it's used for multiple processes?
Usually I see it as a binary, and the reason for that is most people, when they think of it, you can do a counting one. Most people just use a simple mutex. All right. It's important that you can understand that you can still go into deadlock, and that depends on how people write their semaphores. If you or use semaphores, if they use it incorrectly, you can still have it. Let's see. S and Q could be 2 simple. Let's see. Semaphores. So he's waiting on S. He waits on Q. He waits on Q. He waits on S. They're both waiting on each other, or maybe someone finally. He's waiting on Q. Let's see what we got here. Waiting on Q. He would signal both. No, this one's fine. Oh wait, no it isn't. Hold on.
Wait on S.
Yeah. This is okay, except for if you do this. Because, let's say he gets executed, he signals S, which was meaningless, and signals Q, so let's say P1 goes to here, so he can wait on S. And then, no, he can execute. What's the problem here? Because once he signals Q, oh no, this is a semaphore. This is not a lock. So when he signals S, and he's waiting on Q, nothing happens. Because we're using semaphores here. Because he's trying to signal S to wake up someone, but he's waiting on Q, so he's still waiting for someone to signal him. So it's kind of a wasted signal. There's no one
Yes,
woken
yeah.
up. And then he would signal Q, he would go to wait on S. And the problem here is he signals Q, but he jumps up to wait on S. Hold on, it's now.
Both are waiting on S then, at that point.
Well, hold on. Okay, let me go slowly here. P0 is right here. Right? P0 is right here.
Signal
P1 is up here. Everyone good at that stage?
No.
All right.
No,
No?
It's SQ at this moment.
wait Q.
They would be -1.
Is only P0 processing right now?
I thought they were initialized to 1.
Yeah.
Okay, they're 0, sure. Sorry, 0. I mean, they're both 0. Thank you. They're both 0.
So he signals S, that makes S 1.
All right, good. We'll put Q over here and S right here. So S is now 1, Q is now 0. All right, so he's down here. Can P1 do anything?
No,
No.
because Q is 0.
All right, so now he's going to signal Q, which makes Q equal to 1. Okay? Let's say he goes up to here. He doesn't execute yet. P1 executes first. Can he do something?
Yes, because Q is 1.
All right, so P1 executes, decrements Q to 0,
Wait, how
and then
come
let's,
P0 can we went back up to wait, when it says we went back.
remember,
up to
you can
S.
interrupt at any time, right? The only things that are atomic are the weights and the signals.
But S is already at 1, so when you went back up there at the top, your S was at 1.
Yeah, but let's say he got interrupted.
Oh.
He hasn't executed the wait yet.
He's
Oh,
right here.
okay, gotcha.
Is that better?
Yes, yes.
All right, and then we're going to say P1 is right here, and he gets interrupted. So P0 jumps in, and can he grab S?
No.
S is 1.
Yes,
he can grab
he
it.
can.
He can grab S. So then he's 0. Is anyone going to be able to continue?
Nope.
No, because we're both waiting for it, nothing's gonna set it.
How do you easily fix this?
Don't wait on 2 functions.
Timer.
Or 2
That's one way to do it. Don't wait on 2.
On time.
But let's say, how can you fix this while still waiting on 2 different things?
Timer.
Because sometimes you may need both resources. The problem is the order. If they both waited in the same order, it would be okay. At least in this example. There's other issues that can come up, but in this example, we're okay. Let's say we're down. He is still right here waiting. Or I should be a little more specific. So he's waiting on S. This guy can signal S. Change it to 1. And P1 could execute, and then he'd be waiting on Q, right? Well, let's just continue on because I'm just trying to show you that, hey, look, everything's cool. This guy goes on, can signal Q. All right, so Q is now 1. And then he would jump, let's say in our previous example, he got interrupted. Well, P1 can grab S now because it's available. So, and let's say for the sake of argument, he gets interrupted before waiting on Q. So P0. P0 can grab S because P1 already grabbed it. And now that P1's already grabbed S, so he has to eventually get interrupted. And now P1 can grab the weight, grab Q, and continue on to the critical section. In this example, just flipping the order fixes your problems.
Would you flip the signal as well?
Wouldn't matter.
Yeah, it would be good programming practice, but I don't think in this situation it matters.
Okay.
The waiting part is where the order really matters. So starvation is that infinite blocking we were talking about, and priority inversion is what happens when a lower process prevents a higher process from executing because it's holding onto a lock. Because why is that inverting priority?
Because the higher process doesn't get to go.
Right, because the lower process is forcing the higher one to go on a wait queue. That is a scheduling process or problem.
So that, by flipping it, we're fixing the deadlock problem.
Yes.
Okay.
Or starvation problem.
Starvation,
Or
okay,
dead-
starvation, sorry.
That's starvation. In this case, the starvation was causing deadlock.
Okay, gotcha. But could you do on something like that, if any one of your processes was running starvation, could you have a counter for, like, say, to find out, okay, hey, all of a sudden I'm in starvation, I need to have a counter, and
How would you know they're starving?
if they wait too long, I'm saying if I have a wait too long,
Okay.
if all my processes are in a wait stage, and I have a counter and I have nothing going, then I can just say, okay, I can just knock my process off, either interrupt it or just reset it back to the queue, right?
I'm trying to see.
But what I'm saying is you could have a counter so that you do not wait too long. What I'm saying is,
Then how would you distinguish? Oh, let me ask it's a simple question. Then. How would you distinguish between waiting too long and a timeout error? The network connection just went down. How would you distinguish between taking too long and your network just went down?
Okay, then maybe not the timer, the number of times you've actually set a lock or set a signal.
You can keep thinking about it. If you come up with something, talk to me, but
No.
people have looked at this a very long time. I can't sit down and prove to you that you will never find something due to the complexity of this problem, but it's one of these situations like MP completeness,
Oh,
People have
yeah.
been working on it for decades. We haven't really, come up with something. Although there are a couple of data structures that don't require locking and are thread safe, kind of,
Definitely gonna move on.
but we're not doing that here. Okay. Good question. Any others? This is going to be the mega long lecture. Okay, we'll stop here because we're going to go into